Welcome back to learnpiezo.org, and today we're going to be continuing our ultrasonic cleaner series. Today I'm going to describe two methods of measuring capacitance. Now, one method is much more relevant than the other one, but it's also important to and interesting to measure the other property. So you can see for the last two videos, including this one, our focus is just to understand this transducer. What can we measure? What properties does it have? Then hopefully when we get into the actual meat of putting the transducer and doing some programming, maybe in Python and whatnot, and probably eventually introducing our Arduino, and finally putting this ultrasonic cleaner on the on the beaker or whatever we're going to be used for cleaning. We'll just be able to troubleshoot and know what we're getting into. So today we're going to be measuring the capacitance using two ways. So the first way of measuring capacitance, we're going to be exciting the piezoelectric. So again, this is a familiar picture from lecture B, I believe. So we have our USB oscilloscope, and we have this is the voltage probe, this is the power. So we start out with this, we're exciting the transducer here. A current is flowing through. There is actually a resistor here around which there's a voltage probe. So we're measuring the voltage over a resistor, which is the current. Good job. So which is the current. So now we have, and we have this, the negative terminal or the ground terminal of the excitation channel. Obviously you have to make a complete circuit, so you attach that at the end. Here's a little close-up picture. We have the transducer, and then we have the voltage probe over the resistor. In this case, again, the resistor is 325 ohms. If that doesn't work, I'm just going to change it. So the whole purpose of this is to measure the capacitance, which we usually call this C or C naught or something of that effect. And if we measure the voltage over the resistor, we get current, which we'll just call I right now. And for a capacitor, when you excite it at a certain frequency, let's call that frequency omega. When you excite at a certain frequency, it has a certain impedance. Impedance is sort of resistance to a alternating, a cyclical voltage. So if you apply a cyclical voltage of a certain amount, you will get current according to the impedance, assuming there's only, let's say, capacitance, or only inductor, or only resistor. When you have a complex arrangement, you use complex numbers. Interesting, huh? So we have this arrangement of Z. The same thing, V equals IR. And the amount of current you get depends on frequency. And if you wanted to understand more about capacitance, look at my lecture series. I believe the second or third lecture I describe what capacitance is in one of the parts of the lecture. So the impedance here, so we're going to be measuring current, and the current is going to be voltage over the resistor value, which is 325. So we measure the voltage, we can get the current. And then we have here the impedance. We assume that the impedance or the resistance value is quite small in comparison to the capacitance or the impedance produced here. So the impedance produced here is going to be about 325, and these, they interact with each other in a complex way, but we don't have to worry about that because we're going to assume the effect of this is much smaller. However, this resistor is useful for measuring the current. Okay, so we'll be able to measure the properties of the transducer by measuring the voltage of an external component, because we assume that it doesn't affect the current, but it can be used to measure it. So the impedance for a capacitor, I'll write ZC, is equal to 1 divided by omega, and omega is 2 times pi times the frequency, which we're going to be using 1 kilohertz at present. If we find that 1 kilohertz does not produce a large enough current or voltage across that resistor, we're going to up it to maybe 5 or 10 kilohertz, and that times the capacitance. So we'll be getting the capacitance directly out of this. So let's go over now to our Picoscope friend. We open the Picoscope program, and remember we have the experimental setup shown here. So here we are, our Picoscope program here, and so we have some alright, so let's just put this on to signal on 1 kilohertz, amplitude 2 volts. Okay, and sine square, no, we want a sine wave. We want it to be repeat. And I think we're going to probably measure a really small voltage here. So the first thing actually I want to do here is I want to get a signal that we are familiar with. So let's just go and do 30 kilohertz. Because I just want to see now if everything is connected properly here. Oh, oops, I'm not connected properly. Yes, this is one reason why it's not working. I show you pictures from old experiments. That's my issue. And then I don't have the exact, okay, so we're going to do a roll with 1 kilohertz. Let's just see if you can find it. Let's just go with 50 millivolts. So we cannot find it. Let's do auto setup and see if we can see if that will help us determine and get some value. I don't see anything right now. Let's that's a little too fast actually. Okay, that's okay. Let's because 1 kilohertz is obviously 10 milliseconds per division, so let's just increase this to 30 like we had before. Okay. Sorry, it turns out that I keep doing I keep having some loose wires. So okay, after resecuring my wires, this is what I have. Now what does it exactly mean? Doesn't seem like a nice but since it doesn't seem like a very nice signal, we can clean up the signal a little bit. I don't need to zoom in. I should probably use the best resolution I can. So let's get in closer. And let's not do auto, let's do repeat. And let's not do that either. Let's lower the, okay, the signal is here. Let's increase the number of bits to 10. That should get us a better signal. Or we can also increase it to 12, but that reduces the amplitude a little bit. So let's increase it to 10. Okay, just so we can get a little better signal here. It's a little bit blotchy. But here we have a voltage value which is being read over that resistor. We mentioned, I'll just bring up that resistor picture here. So we're measuring the voltage across this resistor, and 325. So let's start to do some calculations. So resistor, 325. And that's going to be in the unit of ohm. Okay. Then we have to determine what the amplitude is. And there's many ways probably you can do it. Usually you add a measurement. And let's do, can't do amplitude. The amplitude is going to be about 10. Peak to peak. Let's see, peak to peak. Okay, amplitude is about 10. Peak to peak is about 30. right? It's about 28. Oh, here we go. We have an average here, 28.1 millivolts. So amplitude, or we can do peak to peak, as long as you keep everything to peak. So all right, voltage resistor peak to peak. What is that? 28.1 milliamps. So e to the minus 3. And then voltage total. Just because the voltage we said the voltage total was, well, we set it to 2 doesn't mean it's actually 2. So it's better practice to actually measure it here. And let's obviously I should go to at least plus 2. So the peak to peak value is 3.50, which is pretty close to what we had before. Okay. Oh, sorry, 3.95. So it's a very slight reduction, and there's also peak to peak voltage total, peak to peak. So now what? What's the current? Peak to peak. Current peak to peak. Okay, voltage divided by resistance is current. So that's the peak to peak current. Okay, and what's the impedance? Now impedance is not a peak to peak thing. Okay. If you divide by the same peak-to-peak units, or you divide by RMS over RMS, peak-to-peak over peak-to-peak, amplitude over amplitude, that part of the unit cancels out. But you know, the voltage and current unit, the ampere, volts over amp, that turns into impedance or resistance. So what is that here? So the current, the total voltage here, divided by the current there. So that is going to be the 45,000 is going to be the impedance at 1 kilohertz. So frequency 1000, right? I said 1000, didn't I? Yes, 1000. Okay. So frequency is 1000, and if you can remember from before, it's really nice. I can still write in this program. Well, it's actually not letting me write. But okay, so the Z equals 1 divided by omega c. So basically what we have to do is basically we multiply that, so 1 over z times omega equals c. 1 over z times omega is the frequency times 2 times pi. You gotta put those parentheses. That's good. That is the capacitance. 3.448 nanofarads. Alright? And that's at 1 kilohertz. Now we can also measure the capacitance at different frequencies. Okay, we can measure the lower limit is going to be based on, so I might just describe a little bit about capacitance. The lower limit of a piezoelectric, okay, what am I doing here? So let me just make a new slide and explain a little bit about piezoelectric capacitance. Now, if I were to tell you the capacitance of a piezoelectric element, and let's say the driving frequency is much less than the resonance frequency, this is a must, we can assume that. And I'm going to draw not the impedance versus frequency, not the current versus frequency, but the capacitance value that we just measured by dividing by, taking the reciprocal of impedance times omega. So capacitance for a perfect capacitor, maybe like a ceramic disc capacitor or something like that, you would expect that the capacitance versus frequency, right, omega, doesn't change. However, in reality, the capacitance is based off of microstructure and other physical phenomenon. For electrolytic capacitor, at very low frequency, they hold a lot of charge. They have a lot of capacitance. But you know those ones that look like this? Those like cylindrical ones? Those are electrolytic capacitors, and they have very probably good performance at low frequency but bad at high. Ceramic capacitors, also piezoelectric can be included. They have a good high frequency response, but they do have some you could say space charge, which gives them a bit of a higher capacitance, lower frequency, and then they'll settle out. So that would be like a piezo. They'll settle out, and then at very high frequencies like gigahertz, then they'll dip down as well. So this is the piezo capacitance, but we're still assuming the resonance frequency is much higher. There's going to be a lot of junk going on all over here because of that resonance frequencies, and many resonance frequencies of any certain piezoelectric element or device. But just know that at a very low frequency, the capacitance is going to be different. And as you're increasing frequency to, let's say, 0 hertz to 100 hertz to 1000 hertz, you may find differences, especially in different single crystal piezoelectrics. But we won't talk about that right now. So essentially, the capacitance at 0 hertz is much larger. So how do we measure the capacitance at 0 hertz? How is that practically measured? And maybe you might have forgotten, but something called the time constant. If we can go back to something like this, if we provide a positive voltage, let's say we hold that positive, let's say we hold 2 volts constant, not time varying, and then we remove this, remove the positive terminal. What will be the voltage at this terminal right here? It'll still be 2 volts. It'll be 2 volts because the charge cannot move through the piezoelectric material to the other side. It'll hold until you short this, or until the leakage, which occurs at a slow rate, until that succeeds in destroying not destroying, but taking out all the charge. But if after removing this, so what do you call it? After removing that terminal, if we took this terminal right there, so let me get a different color, maybe yellow. If we took this terminal right here and then we connected it here, charge would start to flow, as you see that little circle going. So charge would then flow around, current, and the slide would change, not really. So the charge would basically flow around that circle, and the rate and the voltage would then drop as the charge diminishes over the piezoelectric transducer, which is also a sort of a capacitor. So as the charge diminishes and the voltage drops, we can use what we call the time constant, the rate of change, to determine the capacitance at that low frequency. So again, we could have also done this experiment at 10 kilohertz, but as we get to lower frequency, as we drive the system with lower frequency, the current becomes a lot less, because the change of charge on the terminals of the capacitor becomes a lot smaller with lower frequency. Therefore, we don't really have much to measure over that resistor. But right now, what I'm going to do is just show how do you measure the time constant of a piezoelectric. So it's going to basically look like this. Once you short the system, we're going to have an initial voltage here. This voltage, omega, and it'll just drop here, and it'll drop to e to the -1 over the time constant, or e to the time constant. So it'll drop basically at this rate. So the exact formulation, let's just get a pen tool here, and is going to be -e to the -t divided by tau, and tau is going to be equal to the RC, the resistance value times the capacitor. So in this case we have 25, which may be too small, but we're going to calculate the time constant first, what we think it can be around. Then we'll see if this we're measuring a pretty fast source, but we won't. We're pretty fast. We have a pretty good resolution of frequency, so I don't think it's going to be a problem. So we'll just go ahead and measure it. So basically we find this, and this exponential function decays at a certain rate. And once we find the rate at it decays at, then we can measure the time constant, and then since we know what this will be in obviously 1/seconds, the unit, then it actually will be in seconds. Sorry, because this will be unit list. So R times C, we already know R. We can determine C. So again, we're going to charge this with 2 volts constant. Then we're going to remove it. Thus, we are going to determine the time constant. And as this charges and the voltage drops. So let's start this again. So the way we're going to have a DC voltage is that we're going to lower the amplitude to 0 volts, and we're going to increase the offset to I think hopefully we can get to 2 volts. I think it'll allow us to do that. And now you notice that, oh look, there's no voltage across the resistor. That's because there's no sort of current. So we're going to have to move the voltage probe to a different spot. So this is actually the picture of what's going on. I have my positive voltage. I'm just going to keep it at 2 volts by the method I mentioned. I set the offset to 2 volts, and I set the frequency to whatever, it doesn't matter. And at the same time, I increase the amplitude to close to 0 volts as possible. So we pretty much have a 2 volt DC signal. This is the positive, this is the other positive. This terminal, this sort of wire is going to go around. It's going to one side of the resistor. So we have a resistor here, and then we have another wire coming out. I should just have drawn it in black, which is going to the negative side. So basically the negative and positive are connected by a resistor, and we have the voltage being measured across. Eventually what you're just going to end up having, if you want to draw, if you will accept drawing the piezoelectric transducer as a crystal, we're going to end up having this case. So the voltage is, the current is going to, or the charge is going to return to the equal potential state through the resistor, and we'll measure the delay using the voltage, the oscilloscope. So here we have the case. I stopped it, and you'll see I decreased the I have decreased the frequency sampling. I'm going to make sure that everything is connected properly. You'll notice that the value that it's going at is less than 1 volt. So it's less than 1 volt, and the reason why it's the value is less than 1 volt is because the voltage is being directly applied over the resistor, and it draws a certain amount of current at 2 volts, and the oscilloscope is not meant to draw that much current. It's sort of meant to draw power a high, or send a signal to a high impedance source, or sort of pushing the function generator to its limits. So let's just get on with it. Let's decrease the frequency of sampling. Increase the frequency of sampling, but decrease the time base. So we would like to see just auto. Okay. All right. There. That's something. Let's just draw a single trigger. Let's make a trigger signal. Single. Let's make the trigger that. And I don't know why it's sampling. So I'll go all the way until there, and then it'll keep sampling. So we'll see everything. So basically, I'm going to unplug I'm going to unhook. If we have, this is part C, impulse response, the wrong picture. Okay, if we have so I'm basically going to remove this wire right there. I'm going to remove that red, and therefore all the voltage will become equipotential through the resistor. So this is 1 second per division. I know that's too short. I know that's not going to work. And then now let's unhook and see if we did it fast enough. No. This doesn't look much like a nice, what we would expect, so we're just going to make it a little bit smaller. We have 100, so we got to sample a lot faster. So we can either do two things. We're going to increase the amount of samples. Let's see if that helps us at all. So we're going to run single. So let's just, and we should also return this back to 8 bits because we're looking at the change. Okay, a little bit of voltage spike there, and that was all probably due to my fiddling. But won't give up. So I think part of the problem that we're running into is that I was using a too low resistor, and it has a very fast effect. I changed the resistor value, so now we should be able to I bought 10 kilo ohms, 9.72 to be exact, and we will then now run the experiment using that value. So using that resistor. So look how I triggered it. Repeat. This is the level of voltage, plus or minus 5 volts. Now we should do plus or minus 2 volts, and then move this down. Or plus or minus 5 should be fine, I guess. So that is what we have here. So we have that 2, so let's put plus or minus 2 and get a bit more accurate. Now see, that's when I touched it. I'm touching the alligator clip. Now I just removed it. I'm just scraping it off the top. I just removed it. Lifting straight off. Touching, lifting straight off. Touching, lifting straight off. So once you get a nice one like this, so I sort of like this, well actually it's not that good. So I just kept tapping it until I got values that I'm happy with. Not the most precise way to do it. I'm sure there's a way to offset the scale, but I didn't do that. So let's take a look at what formula we need to understand the rate of decay. So the time constant is equal to the time that's around 2 volts to 67% of the final value. Sorry, 63%. That would be 63%. So going back to this, let's just zoom in a little bit here. This is going to be the important part. Let's get this point here. We're going to say the value is 1.878 volts. We'll say the cutoff. I mean, it's hard to determine exactly when the cutoff was, but we'll say the cutoff was negative 47.53 microseconds. Let's get this going there. Negative 47.53 e to the minus 6, 5 microseconds, and 1.869 volts. So 1.869. Okay, that was a T0. T1 would have been, okay, so let's just do that multiplication. The multiplication is 0.69. So 0.69. Just for curiosity's sake, where does it end up really? It ends up about 0. The final value is it's sort of negative, so it hovers between 0. So 0.69 was the value that we wanted. Okay, let's find it. Not there. Here. Okay, 0.69. No, not there. There's some 0 right here. Well, that's as close as you're gonna get. 0.69. 4.7. Negative 13.96 microseconds. Negative 13.96 e to the minus 6 microseconds. Delta t. The difference between these two times. So the initial time minus the before time. That's the time difference. The resistance value is 9. What was it again? I told you it, so I'm just going to go to my multimeter. Sorry for all these stops in the videos. I don't have by 9.63 kilo ohm, 9.63 e to the 3. That's kilo. So capacitance. So delta T, that's actually the time constant. So I mentioned that the time constant equals R times C. Okay, if time constant equals R times C, then the time constant divided by R equals C. Hey, what do you know? We got actually pretty close value. The time constants are very similar, but this is not always true. I've done the experiment other times with piezoelectric elements themselves, and it hasn't been true. But for whatever reason, here it's true of 1 kilohertz and that frequency. So pretty much everything I told you seems not to be true, but but anomalies happen. So normally you'd expect the DC capacitance to be much higher, a good amount higher, maybe like 4 nano-ohms, but in this case, or nanofarads, sorry, but in this case we're not finding it. Sorry, what can I say? Alright, so that finishes this lecture, this part. I will see you next time for part E, I believe.